Welcome to the deep dive. Today, we are taking the ultimate shortcut into a concept that really underpins the trustworthiness of our entire digital world. Explainable AI, or
Ah,
XAI.
mhm.
We're diving deep into the heart of that infamous black box problem, that moment when a highly accurate algorithm spits out a decision and we have absolutely no idea how it got there.
It's the critical pivot point in modern machine learning development. I mean, for decades, the mantra was simple, right? Predictive accuracy above all else.
Right.
But as models became these massive, opaque networks, think sophisticated deep learning systems, we realized we had sacrificed comprehension for performance.
So our mission today is to define the tools that are prying open that black box.
Exactly. Specifically, LIME and Esche,
Hmm.
and to really analyze their reliability
Yeah,
and the critical real-world compromises they force us to accept.
that's right. Our goal is to move past simply accepting a prediction to truly understanding the why. Was the decision fair? What combination of features drove the result? We need to look at the mechanics of these leading explanation techniques, examine how they hold up under stress, in real world and synthetic simulations, and most importantly, understand the incredibly high stakes involved when these systems are deployed in life-changing situations.
And the stakes truly couldn't be higher for you, the listener, and, well, for society as a whole. These AI systems are no longer just benign recommendation engines suggesting movies.
Not at all.
They are making high-stakes, life-altering decisions. We see them operating in healthcare, determining necessary treatments, in finance, influencing creditworthiness and loan approvers.
And even in judicial and governmental processes.
Right, influencing bail decisions or arrests. And a lack of transparency in those contexts is not just a technical failing. It radically increases distrust in technology and raises massive legal risks for the organizations deploying them.
Because if a regulated organization can't explain the decision, it can't audit it, it can't defend it.
It can't. Simple as that.
Okay, let's unpack this core issue then, the black box problem. Why exactly do these complex models like, gigantic neural networks or massive random forests, why do they defy scrutiny just based on looking at the inputs and outputs? It's not like the code is encrypted, the logic is just too dense.
That's precisely the issue. The mapping function within these models, that relationship between your input X and your output Y,
Mhm.
is just too complex for human cognition to follow in a linear way.
I see.
When you build a system using millions of interacting weights and biases, and they're distributed across hundreds of layers,
Yeah.
just observing the behavior, input X leads to output Y, gives you almost zero visibility into the system's inner workings.
So you see the beginning and the end, but the journey in the middle is just gone.
It's gone. It's a journey through a high-dimensional space far beyond our ability to visualize. And that opacity, that's really the main challenge for AI practitioners, especially in regulated industries where accountability just isn't negotiable.
So we need specialized vocabulary to address this challenge, and our sources highlight a really critical distinction between two terms we often confuse: explainability and interpretability.
Absolutely. This distinction is foundational. Think of interpretability as the how. It refers to the technical visibility and a deep understanding of the inner logic and mechanics of the AI model itself.
So how the components, the weights, the nodes are mapping the raw input to the final output.
Exactly. Can you understand how all those pieces work together? This is primarily a technical consideration. It's what engineers need to debug, to optimize, or to ensure the system is learning the right internal features. It's all about technical transparency.
Then explainability is the why.
The why. It's the ability to describe the behavior of the system, often focusing on a single decision in simple, understandable language to humans. It's answering that specific question: why did the model make this particular prediction for this individual?
So it's about the cause and effect mapping.
That's the key operational difference.
Huh.
A model has high interpretability if it's an intrinsically simple structure, like a linear regression model. You can literally read the coefficients to see the exact mechanism.
But a complex, deep learning model has what? Poor intrinsic interpretability.
Very poor. Its inner mechanics are just too dense to map one-to-one to human concepts. But, and this is crucial, that high-performing complex model can still be made explainable. We can use post hoc methods, tools we apply after the model is trained, to extract those meaningful, human understandable connections.
Okay, let's ground this with the HR employee health model example. Let's say we have an AI model predicting employee health risks based on factors like age, business function, past health, and participation in work culture initiatives.
Right. And if the HR team wants to intervene to improve health, they can't control age or past health. They can only control decisions related to the work environment.
So, if the system is designed to be explainable, it helps HR discover the precise cause and effect of their actions. It might show a strong positive correlation between decisions that promote positive work culture and, better employee health. It tells them the why.
The why is that your investment in culture is strongly driving better outcomes.
Exactly.
Okay.
Yeah.
And if that system is highly interpretable,
Now you're revealing the specific granular inner logic. It might show that for this particular model, the internal weight for past health conditions is 50%, business function is 30%, and in-office duration is 20%. That's the how.
that's the technical breakdown.
It is. It's for the engineers.
Yeah.
So for the HR director, the how the specific node weights isn't really a business requirement. But the why, which features correlate to a positive prediction, that is absolutely essential for taking action.
Right, because complex models generalize and perform so much better, but they are black boxes. So we have to sacrifice that intrinsic interpretability to get superior performance. Precisely. And this brings us to the structure of how we achieve transparency. The taxonomy of methods.
The map. We need the map to navigate this landscape. So we're looking at two broad categories of transparency techniques.
The first category is interpretability by design, or intrinsic interpretability. This means you constrain your search for models to only those that are simple and transparent by nature. Think linear regression, logistic regression, or small, shallow decision trees.
The model structure itself is transparent. The logic is easy to audit. But if we need the power of, say, a random forest or a deep neural network, we have to abandon that and move to the second category, post hoc interpretability.
Correct. These are methods you apply after the complex model has been fully trained. And within post hoc methods, we divide them even further. You have model-specific methods, which only work for one type of model, like analyzing learned filters in a CNN or calculating Gini importance in a random forest.
And then the highly versatile methods that are the focus of our deep dive, model-agnostic techniques.
Model-agnostic methods ignore the model's internal mechanics entirely. They're inherently flexible because they only interface with the model using the inputs and outputs. They treat the deep learning model like a true opaque black box.
The approach is often summarized by the SIPA principle, right?
Yeah, SIPA. Sample from the data, perform an intervention on the data, get the predictions for that manipulated data, and then aggregate the results. This approach gives us immense flexibility. Lime and A-shape all fall squarely into this highly flexible post hoc model agnostic category.
Okay, let's dive into the specifics of LIME, which, again, stands for Local Interpretable Model Agnostic Explanations. This approach, proposed in 2016, is all about explaining an individual prediction using a local surrogate model.
The intuitive idea behind Lime is incredibly pragmatic. If you want to know why the black box classified a specific data point, let's call it Math BFAA Joy, in a certain way, Lime doesn't try to unravel the millions of weights inside.
Yep.
Instead, Lime starts systematically poking the black box. It creates small variations or perturbations of that data point, Math BFX, feeds them back into the model, and just observes how the predictions change.
It's the closest thing we have to saying, tell me what happens to the output if I shift this one dial just a little bit.
Precisely. Lime generates a new synthetic data set. It's composed of these perturbed samples and the corresponding predictions made by the original complex black box. Then, on this small, newly generated local data set, Lime trains a weighted, simple, interpretable model, something like a lasso regression or a shallow decision tree.
Right. We have the 5-step recipe for how this works. It's worth running through it because it really explains the core mechanism.
Okay, so step 1, select the specific instance of interest, Math BFX that needs the explanation. Step 2, perturb the data set around Math BFX and get the predictions from the original black box model for all these new varied data points.
And step 3 is the crucial weighting phase. The new samples have to be weighted based on their proximity to the original instance, so points that are mathematically closer to Math BFX get a much higher weight. They influence the local model more.
Significantly more. Then step 4, train a weighted, interpretable model, we'll call it Twyler, on this new locally weighted data set. And this model dialer is fundamentally simple.
And finally, step 5. You explain the original complex prediction simply by interpreting the structure of that local simple model, $. Since $, is intrinsically interpretable, its coefficients or its splits provide the human-readable explanation.
And the critical constraint here is local fidelity. The learned local model $2 must be a very good approximation of the machine learning model's predictions locally in the immediate neighborhood of MathBFX.
But, and this is the beauty of it, it is absolutely not required to be a good global approximation.
Not at all. It could be wildly wrong 100 yards away, but it must be accurate right here. This allows us to use an extremely simple model to explain a tremendously complex decision.
That makes intuitive sense. A small local area of a complex curve can often be accurately approximated by a straight line, but you wouldn't use that same straight line to describe the entire curve.
That's a perfect analogy. The sources formalize this idea in the mathematical compromise Lime seeks.
Okay, let's look at that. Lime is trying to find the simplest possible explanation model, $, that minimizes a loss function, $. And this loss measures how close $'s prediction is to the original complex model's prediction. Is that right?
Exactly. It's trying to minimize this equation. $, b up to m plus omega g. The first term is that local fidelity loss, which we want to be small. The second term, omega g, is the model's complexity, which we also want to be small.
So it's always trying to strike this balance.
Always. Get the most accurate local reflection of the black box while minimizing the number of features you use to keep it human-friendly.
I noticed in the recipe you mentioned using lasso regression as a common choice for the surrogate model, Jellowers. Why is that preferred over, say, a standard linear regression?
Because lasso regression naturally facilitates sparsity, which is essential for human-friendly explanations. Lasso includes what's called an L1 regularization term in its optimization. This term basically penalizes the size of the feature coefficient.
So if a feature's weight is small enough, the lasso penalty just forces it to become exactly 0.
Exactly. It effectively drops the feature from the model entirely. So the regularization parameter in lasso acts as a dial for simplicity. If you want an explanation based on, say, a maximum of 3 features, you can tune the lasso model until exactly 3 features get non-zero weights.
So it ensures the explanation stays selective, concise, and manageable for a human.
Yes. It's a core component of Lime's design philosophy. I mean, an explanation is only useful if it's simple enough to be understood. If you present a doctor with an explanation based on 50 features, it's useless. If you give them the 3 most influential features, it's actionable.
And the power of Lime, then, is directly linked to the generation of those variations, the perturbation of the data. And that technique has to change radically depending on if you're analyzing a spreadsheet, a news article, or a photo.
It absolutely must. For tabular data, Lime creates new samples by perturbing each feature numerically, often drawing values from a normal distribution. For text and images, you can't just shift values slightly. The approach shifts to turning components, like single words or image superpixels, on or off.
Which lets the local model see how the prediction changes when those specific components are removed or retained.
Right, which directly contributes to its feature attribution logic.
Let's connect this theory to practice with some concrete examples. Lime's model agnosticism lets it work across all 3 major data types: tabular, text, and image. Let's start with tabular data using the classic penguin classification example.
Okay, so imagine a model, let's say a complex random forest, trained to classify a penguin as either male or female based on body measurements like flipper length and bill depth. When Lime is asked to explain why a specific penguin was classified as male, it generates thousands of slightly varied synthetic penguins in that local neighborhood.
And it trains the simple linear model dollars on those variations. So what did the results show? What were the feature effects for individual classifications?
The explanations show that for certain individual penguins, features like a higher body mass and a longer bill were consistently associated with a lower probability of being classified as female.
Which makes intuitive biological sense. Larger penguins are often male.
Right. But the local model provides the exact quantitative impact for that single instance. For example, it might say something like, this individual is classified as male because its body mass of 5,400 grams increased the male probability by 0.35, and its bill length of 60 millimeters increased it by 0.15.
This brings us directly to what the sources called the elephant in the living room for tabular Lime, the neighborhood problem.
This is Lime's most serious technical instability, especially in high-dimensional tabular data. Defining a robust, meaningful neighborhood around the point of interest it's excruciatingly difficult. Lime uses a specific mathematical tool called an exponential smoothing kernel to define proximity.
Okay, walk us through what that means for the explanation.
So the kernel width determines the size of the neighborhood. A small width means only extremely close. Similar instances influence the local model. A large width includes points that are further away.
And the arbitrary choice of this width is the problem.
It's a huge problem. The popular Python implementation sets the kernel width to 0.75 times the square root of the number of columns. The source material points out that the origin of that 0.75 factor is obscure, and this selection is a major unsolved problem.
And why is that arbitrary choice such a huge issue? What's the risk?
The explanation is hypersensitive to it. I mean, if the kernel width is too narrow, the local model might overfit to noise and give you an unstable explanation. If the width is too wide, the local explanation might incorporate global trends that run contrary to the local decision boundary.
So it could actually flip the explanation.
It could flip a feature's attributed effect from positive to negative, totally misleading the user about the model's logic for that specific point. It's a huge instability issue.
Wow. Yeah, if the core interpretation depends on a parameter that seems to be plucked from thin air, you really can't reliably trust it in high-stakes regulatory or medical situations.
It creates serious caution. It forces many practitioners to move toward alternatives for tabular data. But let's look at text, where the perturbation mechanism is more controlled and that neighborhood problem is less acute.
Okay, so for text data, like classifying YouTube spam comments, the mechanism shifts from numerical perturbation to just removing words.
Correct. You start with the original text. New, varied texts are created by randomly removing subsets of words. The dataset for the local model is represented by binary features. 1 if a word is included, 0 if it's removed. The proximity weight is calculated based on how many words were removed.
The fewer removed, the closer it is.
Exactly.
In the YouTube spam classification example from 2015, analyzing comments from music videos, what did Lime reveal about specific spam triggers?
So the black box model was a deep decision tree, and Lime was applied to explain why comments were classified as spam. For a spam comment like, "For Christmas song, visit my channel." Lime estimated a high positive weight for the word channel.
So that word strongly indicated the spam class.
It confirmed its dominant role in the prediction. The explanation for the human is instantaneous. The model flagged it because it saw the word channel.
And what about for a legitimate comment, something like PSY is a good guy, which was correctly classified as not spam?
For that specific instance, Lime estimated no non-zero weights. This meant that randomly removing any of those words, PSY is guy, it didn't change the model's prediction that the comment was legitimate.
Which indicates the model was robust for that specific input.
It was. Lime efficiently isolated the reasons for classification, or lack thereof, providing a clear, human-understandable reason based on word presence.
Okay, finally, let's turn to image data, where we're dealing with thousands of pixels instead of words or columns.
Right, if you just perturbed individual pixel values, the network prediction usually wouldn't change much. So Lime uses a technique called superpixels. This is an image segmentation process where interconnected pixels with similar colors or textures are grouped into meaningful segments.
So the perturbation involves turning these segments on or off.
Exactly. Turning them off just means replacing the segment with a uniform color, usually gray. And by observing how the neural network's prediction changes when certain superpixel regions are visually blocked out, Lime isolates the regions responsible for the classification.
The source material provides a great example of an image misclassification. It was baked bread that was categorized as a bagel.
This is a fantastic illustration of Lime explaining the model's internal logic, even when that logic is wrong. So the Inception v3 network was shown an image of baked bread in a bowl. The top prediction was bagel, with a high probability.
And Lime was used to explain this prediction.
It was. And the explanation showed the crust and the center of the baked bread highlighted in green, meaning those specific superpixel areas increase the probability for the bagel label.
So even though it wasn't a bagel, it didn't have the whole. Lime showed the network was focusing on the appropriate visual cues, the baked texture, the brown color, the shape.
It tells us the network learned to classify based on texture and shape features, which is reasonable, but incorrect in this case. The explanation, while not confirming accuracy, confirms the model's reasoning strategy, which is the whole point of XAI. Lime's great strength is that it's model agnostic, works across these diverse modalities, and provides concise, human-friendly explanations.
That versatility is Lime's strength, but we have to return to its major weaknesses. These are critical for anyone relying on these tools for high-stakes decisions. Beyond the serious, unsolved neighborhood problem for tabular data, two other major issues erode trust. The first one being instability, which is a term that worries me profoundly when we're talking about life-critical applications.
Instability means a lack of reproducibility. Researchers have shown that if you check the explanations for two data points that are mathematically almost identical, the explanations can vary greatly.
So it's not consistent.
It's not. And more simply, because Lyme relies on random perturbations and sampling, if you repeat the analysis for the exact same data point 100 times, you may get 100 slightly different explanations. If the explanation changes wildly every time you run the analysis, it's difficult to trust its output when a patient's diagnosis or loan approval depends on it.
That makes Lyme sound less like an objective measure and more like a sensitive heuristic that relies heavily on luck and the specific random seed used during sampling.
It does. And adding to that, there's the vulnerability to manipulation.
Which is maybe the most dangerous aspect.
It could be. Lyme explanations can be strategically manipulated by data scientists to hide existing biases or to justify a decision retroactively. This falls under the umbrella of adversarial machine learning attacks on post hoc explanation methods.
So if an explanation can be engineered to conceal bias, then its utility as a critical auditing tool is severely compromised.
It is, and it demands critical scrutiny from regulators and auditors. These weaknesses, the instability, the arbitrary neighborhoods, and the vulnerability to manipulation really pave the way for Lyme's main rival, SAP or Shapley additive explanations.
Developed by Lundberg and Lee, and they explicitly sought to rectify these structural flaws.
Yes, SAP's central mission was to unify explainers' methods under a sound, theoretically guaranteed framework based on Shapley values, a concept borrowed from cooperative game theory. Specifically, kernel S-shape was introduced as a direct way to rectify Lyme's potential violations of local accuracy.
Before we talk about kernel SAP, we need to understand the intuition behind the Shapley value itself. That sounds incredibly complex, something related to game theory and calculating permutations.
The math is complex, but the intuition is quite elegant. Imagine a team of 5 people collaborating on a project that results in a huge payout. Each person contributed different skills, those are the features, to the success, which is the prediction. How do you fairly distribute the credit for that final success among the 5 contributors?
You can't just divide it by 5 because some people did more work or contributed more critical skills.
Exactly. The Shapley value solves this by considering every possible coalition or every subset of players. It calculates the marginal contribution of a player when they join every possible coalition.
So what happens to the success metric when John is added to a team of Alice and Bob? What about when John is added to a team of just Alice?
You got it. By averaging the marginal contribution of John across all possible orders in which he could join the team, you get his fair, unique credit for the final payout.
I see. So when we map that back to feature attribution in a machine learning model, the payout is the model's prediction and the players are the features. SAP is measuring the marginal contribution of a feature to the prediction, averaged over every possible combination of features.
Precisely. This guarantees a mathematically fair and unique allocation of the prediction back to the input features, meeting 3 important properties: local accuracy, consistency, and missingness. And for us, the biggest property is local accuracy, or local faithfulness.
But doesn't calculating all those permutations, especially in a real-world model with hundreds of features, sound computationally intractable?
That is the central problem. Calculating exact Shapley values is computationally prohibitive for all but the simplest models. And this is where kernel S-shape steps in. Kernel S-shape is essentially a highly refined, mathematically guaranteed version of Lyme.
So it's not a completely new approach, it actually builds on Lyme's structure.
Yes. Kernel SHAP uses Lyme's method of perturbation and training a local weighted linear model. However, and this is the key, it replaces Lyme's arbitrary heuristic weighting function with a highly specific, mathematically derived set of weights called the Shapley kernel.
So instead of Lyme saying, I'll weight points closer to math BFEB more, Kernel SHAP says, I will weight the synthetic points in a very specific nonlinear way that is mathematically proven to recover the exact Shapley values when the linear model is solved.
That is the core technical distinction. Kernel SHAP avoids Lyme's heuristic weakness, guaranteeing that the resulting additive feature attribution mathematically matches the classifier's local behavior. It offers a stronger, more robust guarantee of local fidelity, which Lyme, due to its design compromises, just cannot offer.
This is where we start relying on theoretical guarantees and start looking at experimental evidence. Researchers specifically built a software tool to generate synthetic tabular data sets in 2 dimensions, defined by polygonal boundaries. Why was creating these geometric boundaries so crucial for testing the explainers?
It allowed total control over the difficulty of the classification problem. Real-world decision boundaries for complex models are nonlinear and convoluted. By creating polygonal clusters, researchers could engineer intentionally challenging areas, concave regions, sharp corners, areas of tight overlap, to strategically place test points exactly where Lime's simple linear surrogate model was most likely to break down.
Okay, let's start with case study 1, involving what they called the V-shaped polygon, a classic complex non-convex shape.
So they trained an MLP classifier on this data to classify points as inside or outside. They selected test points, Q1 and Q2, near that challenging inner convex hull area. These points were designed to be very difficult, existing right where the classifier had to make a complex nonlinear decision.
And the MLP classifier correctly predicted that Q1 and Q2 were outside the polygon. For example, Q1 had a 72% probability of being outside. But Lime failed to explain this.
Lime's explanations suggested a direct contradiction. For Q1, Lime's simple local model implied that the specific $6 and dollars of Q1 were actually correlated with an increased probability of being classified as inside.
So it was just wrong. The overall feature attribution did not match the actual classification.
A clear violation of local faithfulness. The local linear approximation was misleading.
It's like the classifier had to make this complicated curve to avoid including Q1 in the V, but Lime's simple line just drew a different boundary right through the V, making the explanation for Q1 appear opposite to the ground truth.
Exactly. Lime's heuristic shortcut approach just broke down because the complex nonlinear decision boundary was too curved for a simple linear model to approximate faithfully, even locally. This instability highlights why Lime cannot be blindly trusted when decision boundaries are complex, which they always are in deep learning.
And what happened when SAP analyzed those same difficult points?
SAP's explanations accurately reflected the model's output every single time. The calculated SHA values consistently showed that the features were pushing the prediction away from the inside classification and toward the correct outside classification. It confirmed that kernel JP was robust enough to maintain local fidelity.
So the researchers then made the problem even more complex by moving to a case study involving overlapping clusters and feature redundancy, which mimics the noisiness of real-world data.
Yes, case study 2 involved two polygonal clusters, PD1 and PD2, engineered to have a slight overlap. They trained an MLP and chose a difficult point, Q3, which lay within the boundaries of both polygons, making it highly ambiguous.
Tell us about the results for Q3.
The MLP classifier determined that Q3 belonged definitively to 2.2 with a high probability 73%. However, Lime's explanation for this P2 decision was highly counterintuitive. Lime's output asserted that the $6 values for Q3 were both in ranges typically correlated with the P1 classification.
Wait. The classifier definitively said $2, but Lime's explanation insisted the features were pushing it toward $21. That's a direct, measurable contradiction.
It's a severe failure of local faithfulness. It is. The explanation provided by Lime did not align with the model's actual prediction for that specific ambiguous point.
And by contrast, SJ.
SAVE's explanation for Q3, which showed the feature contribution towards TPU2, matched the model's output perfectly. It provided a faithful rationale.
And then they escalated the complexity further, testing feature importance in a multidimensional scenario. This is crucial because real-world inputs rarely exist in isolation. They have redundant and noisy features.
Absolutely. They took the overlapping cluster setup and expanded the feature set significantly. They added 2 exact duplicates of the original features, 3 redundant features which were random linear combinations of $6 mixed with noise, and 1 totally uncorrelated noisy feature.
So the explainers had 8 features to choose from, most of which were highly correlated or just distracting.
The results were stark. For a point called Q1, Lime again failed, violating local faithfulness by attributing the prediction of $2.1 to features that were actually correlated with 2.2s. The explanation was just flat-out misleading.
How did SAP handle this chaos of correlated and noisy data?
SAP consistently reflected the classifier's output across all test points, even though it sometimes behaved a little awkwardly. For instance, for one test point, SHA sometimes assigned low importance to the original clean features, $6 and dollars, and high importance to the noisy redundant features.
That sounds like a suboptimal explanation, but it wasn't contradictory, was it?
Correct, and that's the key takeaway. SAP, while potentially sensitive to feature collinearity, splitting the credit between correlated features, it never provided a contradictory explanation that violated the classifier's actual output. Lime's explanations may fail under certain common conditions inherent to complex models. SAP effectively rectifies that disparity.
Our focus so far has been on local explainability, that microscope view of an individual decision. But as the research clearly emphasizes, building trustworthy, ethical AI requires both the microscope and, well, the bird's eye view.
You need both local and global explanations. Local methods like LIME and S-shape focus on individual predictions and are vital for debugging single cases and providing user-facing rationale.
Global methods, conversely, describe the model's average behavior and overall strategy across the entire dataset. They're essential for high-level validation, regulatory auditing, and detecting systemic bias that affects a whole population.
A key global technique is permutation feature importance, or PFI. PFI works by measuring how much the model's accuracy drops when a specific feature's values are randomly shuffled.
So if shuffling a feature, say age, causes the model's prediction accuracy to plummet, that feature is globally important.
Right. If shuffling it causes no change, it's globally unimportant. It tells you which features the model relies on most overall.
Then we have partial dependence plots, or PDPs, and accumulated local effects, ALE.
PDPs show the marginal effect of one or two features on the predicted outcome, averaging out the influence of all other features. For example, a PDP could show that as the square footage of a house increases, the predicted price increases on average.
But the sources noted a problem with PDPs, which is why ALE was developed, right?
Yes.
Yes.
PDPs can sometimes calculate the average prediction for data points that are statistically impossible or extremely rare, like a 10-year-old having a high credit score. ALE rectifies this by calculating the effect of a feature locally within the observed data distribution and then accumulating those local effects. It provides a more robust, realistic view.
Why are these two lenses, local and global, both so indispensable? The financial example clarifies why the global average alone can be so misleading.
Imagine a massive insurance company using a model to predict risk. Globally, using PFI, they might find that marital status is the single most crucial feature overall, accounting for, say, 35% of the model's decision power on average.
That's the global insight they report to regulators.
Right. But now, a specific individual, Sarah, is denied coverage. The global finding about marital status is irrelevant to her. She needs the local explanation.
Absolutely.
So when you switch to a local method like SHAP for Sarah's case, you discover that her denial was driven by an obscure metric like the distance from primary care provider, which was locally weighted far higher than her marital status. You need both to debug the system and to validate its fairness.
And this combination is also critical in healthcare diagnostics.
Oh, definitely. Consider a deep learning model analyzing X-rays for tumor detection. Globally, administrators need PFI and global surrogates to ensure the model relies on legitimate medical features like density and shape, rather than irrelevant data like the hospital's lighting or the patient's race.
To confirm the model is medically sound and unbiased overall.
But locally, the physician needs the specific reason for a single patient's positive prediction before making a diagnosis.
In that case, the physician uses a local visualization method, like a heat map from SHAP values, on that specific X-ray. And the heat map visually highlights the exact lesion that triggered the disease-present prediction.
Right. Local reassurance allows the doctor to trust the AI's flag for this patient, while global analysis assures the hospital that the model's overall decision strategy is appropriate for all patients.
This inherent complexity leads to a deeper philosophical problem, the Rashomon effect.
This phenomenon, named after the 1950 Japanese movie, acknowledges model multiplicity. It means there can be multiple machine learning models that have highly similar predictive performance, say 95% accuracy, but wildly different internal interpretations, feature weights, and logic.
So if Model A and Model B are both 95% accurate, but Model A bases its decisions heavily on Feature 1 and Model B bases them heavily on Feature 2, which model's explanation is the truth?
Precisely. When you face this model multiplicity, it becomes very unclear which model's internal logic should be interpreted and acted upon. We just don't know which interpretation truly reflects the underlying data reality.
The discussion moves far beyond technical debugging when we enter high-stakes domains like healthcare, justice, and finance. Here, the very purpose of XAI shifts. Explanations must be designed to be actionable and contestable.
Actionable meaning they provide clear, pragmatic steps a person can take to change the outcome. And contestable, meaning they provide the information necessary for a person to push back and legally challenge the AI's determination.
This is a crucial point. The opaqueness of AI systems inherently shifts power. By making decisions non-transparent, they shift power toward the organizations deploying the systems, reducing the agency of the people subjected to those decisions.
Right. We need to design explanations that account for the legal concerns of those impacted. The sources identify three key stakeholder groups, all of whom have distinct legal needs.
First, the decision makers. These are the professionals, physicians, loan officers who act alongside the AI. They're the buffer.
And decision makers have a fundamental legal obligation to act in the best interest of their clients or patients. They need legally salient information to manage their own liability. If a physician uses an in-house AI system, they are typically held fully liable for any harms.
And second, they need to advocate for their patients.
Exactly. They need information to contest improper AI decisions made by other entities, like insurance companies denying coverage. Strong explanations empower them to gather the legally actionable evidence required to push back.
Next, we have the decision subjects, the patients, the housing applicants. They are the most vulnerable.
They're particularly vulnerable because the explanations from Lyme or Esche are often technically complex and geared toward the decision maker, not the subject. The risks are tangible. We have documented cases where insurance companies use opaque algorithms, like NaviHealth's NH Predict system, to deny medically necessary Medicare Advantage benefits to vulnerable populations.
Leaving them without essential post-acute care.
Yes, and outside of the tangible harms, decision subjects bear significant emotional and psychological burdens trying to push back against these unjust decisions. To restore their agency, they need information about their legal rights and mechanisms for contestation.
Finally, we have the legal representatives, the lawyers who step in when harms occur.
Legal representatives face a severe power differential because they often can't compel the discovery or audit of the black box system itself. Public defenders scrutinizing computational forensic software, for instance, frequently face immense barriers to building counterarguments.
So, legal representatives need to understand what information from the AI system constitutes a legally usable, understandable explanation that can be presented effectively in court.
That's the crux. Traditional technical explanations like counterfactuals, if you had raised your credit score by 10 points, the loan would have been approved. They may not be intuitive to judges or juries.
This massive systemic need demands the establishment of legally informed XAI. This is clearly not a purely technical problem.
It requires co-disciplinary analyses where researchers, lawyers, developers, and ethicists actively work together. And a practical starting point is to rigorously analyze existing litigation and harms databases. We need to look at what kinds of situations result in lawsuits and what kinds of harms are being reported.
And crucially, we also have crowdsourced databases that document harms that might not even result in lawsuits but still show systemic problems.
The AI, Algorithmic and Automation Incidents and Controversies Database, or AIC, is crucial here. These databases document harms like regulators doubting Babylon Health's triage system or reports of IBM Watson recommending unsafe and incorrect cancer treatments.
By jointly analyzing these cases, interdisciplinary teams can reveal precisely where the legal, technical, and social systems are failing users.
Which directly leads to clear design opportunities. Ultimately, explanations need to incorporate two critical types of information. First, legally informative information, which explicitly describes relevant laws and liabilities, and second, legally actionable information, which is documentation generated by the XAI system that can actually be used as evidence in a lawsuit.
So the explanation is no longer just a technical output about feature weights. It becomes a piece of critical infrastructure that protects individuals and enables them to contest the system's determination.
That is the ultimate goal of XAI. Ensuring transparency is not just an afterthought, but a foundational element of ethical and responsible system design.
We've taken a comprehensive journey today, diving deep into the black box. We define the difference between high-level explainability, the why, and technical interpretability, the how. We analyzed Lyme, the inventive local surrogate model, and saw its strength across data types, but also its critical instabilities.
Especially that reliance on heuristic choices like the arbitrary neighborhood kernel for tabular data.
And we compared Lyme's heuristic approach to SHIP, the robust alternative built on the mathematical foundations of Shapley values. Through the experimental evidence, we saw that SHAM promises and delivers a guarantee of local fidelity.
It successfully rectifies Lyme's failure to faithfully reflect complex decision boundaries.
Finally, we established that both local explanations for debugging individual cases and global explanations for auditing overall behavior are indispensable. And most importantly, we learned that in high-stakes environments, XAI must evolve into legally informed XAI, providing explanations that are both actionable and contestable.
It's a massive challenge. We've established that explainers like Lime and Esha can be highly useful for making complex predictions transparent.
But the sources also warn that these explanations can be manipulated by data scientists to hide existing biases or justify outcomes after the fact. Given that model accuracy and predictive power are often considered the primary competitive advantage for companies deploying AI, and that an honest explanation might reveal proprietary weaknesses.
What practical oversight or external checks should be put in place to ensure the explanations provided, especially in high-stakes legal or medical contexts, are honest, objective reflections of the model's true logic, rather than just carefully curated, adversarial justifications designed purely for compliance? That is the question we leave you to mull over.